Hi, everyone. Let's continue with our discussion on the more applications of integrals in 8.3. And we definitely see a shift here compared to what we were doing in 8.1 and 8.2. 8.3, you notice, is fluid force and center of mass. So these applications are probably what we really think of when we think of applications. These are more closely connected, happen to be more closely connected to physics. And so we see quite a lot with that. That said, I am no physicist. I There's a reason why I picked math over physics as my major, and so we'll be looking at it definitely much more from the math side of things and the calculus side of things compared to what you might see some of you guys as you're taking your physics courses. Okay. Also, 8.3, you notice there's these two big ideas: fluid force and center of mass. Honestly, this could be two separate sections, and I'm going to treat it like that. So, um, you know, we'll get all the videos here for 8.3, but we're presenting it. Kind of take it as these are two completely separate ideas. Okay, so let's get into fluid force, and we're going to lay out some physics equations here to get us off the ground. So when we deal with fluid force, we're talking about like a liquid that's exerting some pressure. So fluid pressure is where we will start. And we've got this formula here. Pressure equals the density of the liquid multiplied by the depth. So the idea is the depth is like an object that is at some depth within that fluid. So how deep is your object? Maybe in water. So you'll take the depth and multiply it by how dense that fluid is, and that would tell you how much pressure is being exerted on that object. So the deeper you go, the more pressure there is, right? And it also depends on, just how heavy or how dense that liquid is in the first place. A more dense liquid, you're going to experience a lot more pressure much sooner. Okay, so there we go. To give you some variables to represent this equation, we're going to say pressure is capital P. The density of the liquid is this Greek letter rho. Kind of looks like a lowercase p, but it's sort of curved. So you see this kind of like sweeps around. I don't know if you guys are familiar with that Greek letter at this point. It might be your first experience with it. Rho. All right. We use rho for density typically. And then D is depth. So capital P equals rho times D. And then I've got this Pascal's principle. So it's still here in my notes, as you can see, although the more I've been teaching this, I typically skip this idea. So you kind of notice my little note to myself there. Should I just skip this? It's kind of an interesting idea. I've realized over the years that it's not nearly as helpful as, compared to maybe if you were taking a physics course. It turns out we don't really even need to think this deep about it for the math that we're going to do. But, it's here in my notes, so I might as well just point it out. So Pascal's principle says that the pressure at depth D is transmitted equally in all directions. So it's kind of an interesting idea, even if we don't necessarily need it for the math we're going to do. So imagine, like this line here represents some given depth underneath the surface of your fluid. Okay, so here I've got three plates. So one plate is laid horizontally, and we're imagining the pressure right there. One plate is perfectly vertical, and it's going to have some pressure right there. And another plate is like laying sort of at an angle. That's what I tried to depict there. And we're imagining this. So all three of these points are at the same depth. And you notice that the way the pressure will exert itself on those points, it's always perpendicular to the plate. So here we think of it as pushing straight down. While in this case, when it's vertical, the pressure is coming in, you know, uh, from the side. And if it's sort of laying at an angle, then it's kind of coming in again perpendicular to the plate. So you might think, well, does the angle matter? And turns out no. The pressure coming straight down like this would be the same as the pressure coming in sideways or at an angle. So long as it's at the same depth, those 3 points all experience exactly the same pressure. Although we would think of the pressure coming as from different directions, which is very not intuitive at all. Um, but yeah, fascinating. Okay, so where are we going from here? Okay, so we've got our previous equation, pressure equals density times depth. And we're going to go a little bit further with that. We're going to define fluid force. Of course, that's what we're studying. So it turns out fluid force equals pressure times area. If you've taken any physics, you may be familiar with force equals mass times acceleration. Well, that would be for like an object in motion. But when we're talking about pressure, fluid pressure, force is pressure times area. So it's almost like pressure is your acceleration, right? Something's pushing, and the area, the total amount of area that it's pushing on, right, gives you all of the force. Kind of like you're imagining all the little pressures on all the different little points, summed together, would give you the total force exerted on, let's say, a plate that you might submerge in a fluid. So capital F equals capital P times capital A, and now we'll go back and say, okay, but then P was rho times D, and so we can replace that. So force equals rho times D times A. Density times depth times area. Now, as we're still getting used to this concept, I've got an example here that does not involve calculus. So we'll get there very quickly, but let's just pause here. Let's do a non-calculus example of fluid force just to help us wrap our head around this formula and why it would be the way it is. So example, find the fluid force on the plate in pounds. So our units here will be pounds, and we're told that water is 62.5 pounds per cubic foot. So I'm just going to show you the whole problem here. So you'll be given the drawing. In pretty much all of these fluid force questions, you'll be provided a drawing. Okay, so the idea is here, this is the surface of the water. Okay. We've got this plate that is laying perfectly horizontal. Okay, so it turns out if it's laying perfectly horizontal, we don't need calculus. And we know the dimensions of this plate. It's quite large. It's 6 feet by 10 feet. And you can see that it is 8 feet down. And again, it's perfectly horizontal. So every point on that plate is 8 feet below the surface. So if we wanted to know the fluid force exerted on that horizontal plate, we'd say, okay, I know F equals rho times D times A, density times depth times area. So the density, well, they told us right there, 62.5 pounds per cubic foot. The depth is 8 feet. And the area of our plate is 6 times 10, 60. So we just multiply these three numbers. We'll get the total force exerted on that plate. And you can see it's a huge 30,000 pounds would be the answer here. Pounds as our units. You think 30,000 pounds. So there's 30,000 pounds sitting on top of this plate. And even the formula makes sense if you think about it, right? So, what is the depth times the area? So think like 6 times 10 times 8, wouldn't that be like the cubic, or maybe not cubic, but kind of the rectangular prism or whatever it is, like sitting, that's the volume of the water sitting on top of the plate. So going all the way up to the surface all around. If you think of just how much water there is, right? 6 times 10 times 8, and that'd be cubic feet, right? And then we multiply that by the density, and that makes sense. So how much, what's the volume of water sitting on top of the plate times the density of the water? You can even see the units, right? So the feet cubed would cancel out, and we'd get pounds as our answer. 30,000 pounds are sitting on top of that plate. Well, it's a very large plate, 6 by 10. It's 8 feet down, which is, pretty. I would, that's a lot of water sitting up there. So, okay, makes sense. Okay, so how does this translate to using calculus? Show you guys this. If the plate is not horizontal, so I've kind of got my question there. What if the plate is not horizontal? If the plate is not horizontal, then that means there will be a variable depth. The depth will change from point to point. And if the depth changes, then the pressure changes. Because the more deep you are, the more pressure is experienced. And I've got a drawing here that I'm hoping will sort of illuminate what's happening. So imagine this is the surface of your fluid. Oftentimes we use water, although there's a few questions here and there where it's not water. So we're given this, there's the surface. And imagine this plate sort of laying at an angle, right? So it's a perfectly rectangular plate sort of angled down. And I've highlighted two aspects here. So I've drawn, say, a given line there, and I've called it L of y. So that's like a length. And then I've drawn the depth going down to that particular length. And you can imagine, well, if I was to draw that length somewhere else, it would be a different depth, right? Okay, so here's the formula that we'll use, our integral, when we have variable depth. We'll say, okay, then the fluid force equals the density again, and that will be a constant. So that can like come out front of the integral. It's the integral from A to B. So the A and the B would be, the A would be your starting depth, and the B, we can probably, kind of label that as well. So here's A and here's B. Right? D of y, so that's depth, and you notice all these y's. So we typically do these integrals. It's kind of the the convention to do it with respect to y, since we're talking depth is thought of as being vertical. So the depth with respect to y, and so of course at different y values the depth changes. Okay, but we still have d, but now it's a function. And then notice this last part. So before we had area, right? Rho times d times a, right? A for area. Now area is both of these together. So what's up with that? Okay, so it's a length times the infinitesimal width. Okay, so let's just kind of point this out. So the horizontal length, and that's what I've drawn right there. So how long is that at that, right? Because all those points are at the same depth. Multiplied by the infinitesimal little width. So there's an infinitesimal little width to that. So a length times a little width would give an area. So this is still rho times d times a, but now we're thinking of, because it's at any given moment the length changes, we can take the integral this way. And what we're doing is adding up all of those little d times a's, all the infinitely many little depth times areas as we work our way down the plate, as we work deeper and deeper. Okay. Hopefully that makes sense. We're going to do an example in the next video.